So continuing in in chapter 6, and we're in section 6.3, matrices for linear transformation. So we mentioned that if you have if T of x is equal to ax, where a is a matrix, so matrix times a vector x, that's a linear transformation. And now the book asks a very interesting, it seems like a very simple question, and at the same time a profound question. You could represent the linear transformation like this: T of x1, x2, x3 is equal to this whole mess here. Or you could represent it this way: T of x equals ax, which is this matrix times that vector x. And these two, this and this, are two different ways of saying the same thing. So which do you prefer? Which do you like? Well, I mean, I think it's obvious. The second way, the matrix way, is better. I mean, it's simpler to write. It's simpler to read. You know, it says here that it's more easily adapted for computer use. Now I'm gonna confess right away. I'm not really a computer person, but this is what they say, so it makes sense. But either way, it's just more compact and it works kind of more cool. So we're happy with this representation. That's definitely the way we want to say things. And we also want to mention now the key to doing this, to representing a linear transformation by a matrix, is you have to determine how the linear transformation acts on the basis. Once you see how it acts on the basis, that's going to help unlock everything. So let's see what we're talking about here. So the standard basis for Rn looks like this: 1 0 0 0 0 1 0 0 0 da da da, until you get a whole bunch of zeros and then a 1. Now we're calling this column E1, E2, E3, and that's En. Okay, so here's a theorem that's going to be very helpful, and this is theorem 610, which is that if T is a linear transformation and it goes from Rn, N like November, to M like Mike, if that's a linear transformation, and such that for the standard basis vectors EI, now again, EI, that's our standard basis, 1 0 0, so on and so forth. So if T of EI of E1 is equal to this column here, and T of E2 is equal to that column there, dot 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 dot, and T of En is equal to this column there. By the way, whoever makes these dot dot dots, it's a big thing in linear algebra, as you've seen already. Anyway, the M by N, that's Mike by November matrix, whose N columns correspond to these T of EI, meaning these same A's here. So if I take this column and that column and all these columns, just stick them together, just press them all together into one giant happy matrix. So these numbers down here are the same as these numbers up here. So if I do that, then this new matrix A is going to be I guess, express the entire linear transformation. So T of V is going to equal AV for every vector in Rn, not just for the standard basis vectors, but for every vector. And A is called the standard matrix for T. So that's how we construct this matrix A. Let's actually do it in real life. Oh, first let's just show why it works. So we want to show that T of V is equal to AV, okay? So we're going to take our vector, our vector V, we're going to write it in this form: V1, V2, da da da, Vn transpose, which means really the vector was a vertical vector. We're writing now horizontally. But this is equal to, now remember, V1, V2, these are all scalars. But this is really V1 times E1 and V2 times E2, because it's V1 times 1 0 0 0 0, and it's V2 times 0 1 0 0 0. You see what I'm saying? So this just like 2 comma 3 is really 2 times 1 comma 0 plus 3 times 0 comma 1. That's what this whole thing here means. Now, since T is a linear transformation, so T of V1, E1, V2, E2, da 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 is going to be V1, T of V1, V2, T of V2, da da da. But T of V1, we said that's, well, let's just hold on to that. Now, on the other hand, if we look at the matrix product AV, so here's the matrix A, here's the matrix V, here's the vector V. When we do the multiplication, we get A11 V1, A12 V2, da 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 da, and notice that each now this is not a single column matrix. It looks like it's a lot of things because I have all these pluses, but really it's just a single column. It's just a what do you call it, a m by 1 column. So, but I could break this up. Notice that I have a whole factor of V1 here, a whole factor of V2 on this line, whole factor of Vn. So this I could break up into V1 times these guys here, plus V2 times those guys here. But what are these guys? These guys, this is T of V1, that is T of V2, T of Vn, which is exactly what we have up here. So T of V, and AV are the same thing. And that is our awesome proof. So now let's actually do this. And find a standard matrix. So we want to look at a linear transformation. We're going from R3 to R2. So T of XYZ is X minus 2Y, comma, 2X plus Y. So first you have to find the images of the, now, notice it goes up to E3 because we're talking about, when we talk about the standard basis, we're talking about from the domain. Okay, so what is T of E1? Well, take E1, plug it into this formula here. You get 1 minus 0 plus 2 plus 0, which is just gives us 1 comma 2. And what is T of E2? Take E2, stick that into here, and we're going to get 0 minus 2 plus 0 plus 1, which gives us negative 2 comma 1. And for E3, well, 0 minus 0 comma 0 plus 0, so it's just 0 comma 0. So these are so that's our E1, E2, and E3. T of E1, T of E2, T of E3, these guys right here. Therefore, based on the theorem that we just learned, theorem 6.10, I think it was 6.10, that we just did a few minutes ago, the matrix A is going to be this guy right here: 1, 2, negative 1, negative 2, 1, 1, 1. It's basically I take these three guys here, just sandwich them together into one happy matrix. And pal, you see how easy that was? And there we go. There's our matrix. So if I would multiply, now let's just check it here. If I would multiply the matrix A times XYZ, that's going to be this matrix times XYZ, which if you do the multiplication, you get X minus 2Y, 2X plus Y, which is the same thing as what we started with, that T of XYZ is equal to X minus 2Y, comma, 2X plus Y. But just see how it's just so much easier to read. I feel it's just so much easier to read this way. Okay, moving on. Eventually, you get to a point where you can just look at it. Because I see here, I'm looking at the coefficients now. 1, minus 2, plus 5, that's my type row. That's my top row. 2, 3, 2, there's no x2, and then there's a 3. So that's really 2, 0, 3, which is my second row. And then 4, 1, negative 2, there's my third row. So pal, it gets to a point where you can just just give that matrix in 2 seconds. And that is awesome. So let's find the standard matrix for linear transformation. So I just said it's simple. Well, here I'm not going to give you those numbers. I'm just going to describe the linear transformation. So we have a linear transformation, and we're going from R2 to R2, and we're getting it by projecting each point down to the x-axis. So if I have a point x comma y, I'm just projecting it down to the x-axis. But that means x comma y is really becoming x comma 0. So really, I have T of xy is equal to x comma 0. So the standard for this is T of 1 comma 0, and then t of 0, comma 1. Well, and that's very simple because what is t of 1, comma 0 would just be 1, 0, and t of 0, 1 is just 0, 0. So this winds up being my matrix right there, 1, 0, and 0, 0. So if I would take this matrix and multiply it by x by an xy, I'd wind up getting x0. That's really what I'm trying to say here. And that, again, is awesome. And you can use this for all sorts of things, circuitry and all kinds of cool, awesome things. I think I'm going to just stop. I'm going to stop the part 1 video because now this is a little bit of a new topic, composition. So I'm going to stop now and we'll continue next time. Bye, everybody. See you soon.